Good day, everyone. Our topic for this week is atomic and molecular properties, focusing on the quantum numbers. This is inorganic and organic chemistry. I am Dr. Erwin R. Abrencillo. For our learning outcomes for this week, identify the subatomic particles of an atom. Determine the steps in identifying the quantum numbers of elements. Solve problems about quantum numbers. For our lesson outline, we will be having our review of the Dalton's atomic theory. Second, subatomic particles of the atom. Third is the quantum numbers. However, though these are the contents of our discussion, expect that there will be other topics as long as they are all connected to quantum numbers. So let us now begin. So, can you recall your idea about Dalton's atomic theory? So before proceeding to this video, I want you to recall these four assumptions. You can pause this video and then I want you to jot it down on your notes so that later on you can be able to participate in this video lesson. So what are they? First, elements consist of indivisible or small particles known as atom. Um, Many years before John Dalton, there was a philosopher in the name of Democritus who said that there will come a time when a certain matter is no longer be cuttable or considered to be as indivisible. So he called that as atomos. So from that explanation, it was continued by John Dalton, or Democritus served as an inspiration to John Dalton in forming such. So elements consist of indivisible small particles. So second assumption, all atoms of the same element are identical. Different elements have different types of atoms. So for example, oxygen atom is composed of oxygen. Oxygen element is composed of oxygen atom. Meanwhile, lithium element is composed of lithium atom, and so on and so forth. So that means that different elements have different types of atom. So third assumption, atoms can neither be created nor destroyed. So we cannot create atom in the same manner that we cannot create nor destroy matter or energy. The fourth assumption is compound elements are formed when atoms of different elements join in simple ratios to form compound atoms. Now, they do this in a certain proportion or ratio. So that means, let's say, for example, when hydrogen atom chemically combined with oxygen, so it should, to form water, it should be two atoms of hydrogen in every one atom of oxygen. So more than that, or if there will be more oxygen or more hydrogen, so it will no longer be water. Or we can assume that it might not be um, chemically possible. So these are the four Dalton's, these are the four assumptions in the Dalton's atomic theory. So later on, you will realize that these are all connected to the different topics that we are going to discuss. All right? So let us now continue. So let us now proceed to the subatomic particles of the atom. Well, these are basic, no? So protons, electrons, and neutrons. So perhaps you are wondering why we have to include this. So you have to remember that for us to be able to understand what quantum number is, we have to understand first or recall the properties of protons, electrons, and neutrons because these are very essential for us to better understand the content. So, probably you might think basically that these are, protons are positive, electrons are negative, and neutrons are neutral, and these are all correct. But let us add more to that. So, the protons discovered by Ernest Rutherford in 1918 and then was followed by neutrons by James Chadwick in 1932. They found out that the atomic weight or the atomic mass can be found in the nuclear region of an atom. So that means that the mass of an atom is concentrated on its center, which is the location of the protons and the neutrons. Meanwhile, in 1887, J.J. Thomson discovered the existence of the electrons. So they are found outside the atom and do not possess much mass. So that means that the mass of an atom is attributed with that of the nucleus that contains the protons and then the neutrons. So with that, we can be able to analyze these atomic properties. So there are 118 known elements or known kinds of atoms, one kind of each element. All atoms have a nucleus, and an extra nuclear region containing all electrons. So the nucleus of an atom is found at the center. It is not moving, incomparable with that of the electrons. So electrons are actually moving. And the purpose of the quantum numbers actually is for the specific location of the electrons and as well as the shape of the atom. So protons are, of course, we said this a while ago, protons are positively charged. Relative mass is 1,837 times that of an electron. And protons are actually the atomic number of an element. So that means that in one element, there's only one, there is that specific number of proton, which is equivalent to, that is known as the atomic number. So when we say 6C carbon, or carbon has an atomic number of 6, that means that carbon has 6 protons on its atom. And then neutrons, the charge is 0. It is 1,839 times than that of an electron. And protons and neutrons combined, you can be able to get the atomic mass or the mass number of an atom. Meanwhile, another subatomic particle is electron. So it is negatively charged. Relative mass is 1. Electrons determine the chemical properties of an atom. Okay, because whenever there are chemical reactions, we consider the charge of an atom, which is attributed on its electron. Now, there are also cases wherein um, there are cases where there is formation of isotopes. So isotopes are the atoms of various isotopes of an element contain the same number of protons but different number of electrons, of neutrons in the nucleus. So isotopes have the same atomic number and different mass number. So that means that they are of the same element but of different mass. For example, carbon 12, carbon 13, and carbon 14. So all of them are carbon, 6C carbon. Carbon 12 is the common carbon atomic mass. 13 and 14 are seldomly observed. In fact, carbon 14 is the one used in the radioactive dating, the one that used by scientists for them to be able to determine the age of fossils, let's say fossils of dinosaurs. So they use carbon 14, radioactive radioactivity for them to be able to determine the age of a certain fossil, because all organisms, either they are dead or alive, contains carbon. So that's why we are known as carbon-containing organism. Now, when it comes with the atomic mass of an isotope, the average mass of all isotopes of an element weighed according to natural abundance is the atomic mass. So that means carbon-12, for example, carbon-12, 13, and 14. So later, there are more carbon-12 there. So that's why the atomic mass that can be found in the periodic table as organized by the one who made it. So the one declared there is the carbon, it is carbon-12. So for your first activity, I want you to complete this table. So I made the first example for potassium. All you have to do is to get the missing part of the column, no, of the table. So for example, you have to get the element, the symbol of that element, atomic number, mass number, number of proton, number of electron, and number of neutron. Actually, this is very basic, and I am sure that way back in your lower sciences, you were able to make one, no? So, for example, potassium has a symbol of K. Its atomic number is 19. So, that atomic number can be found in the periodic table of elements. And the mass number can also be found there. All you have to do is to round it off, no, round up to a whole number. And then you have to remember that the atomic number is equal to the number of protons. So if the atomic number of potassium is 19, then therefore its proton is also equal to 19. Now, protons in a ground state of a certain element, for example, in potassium, um, protons are equal to the number of electrons. So if protons are 19, then electrons are also 19. Now, it is said that the atomic mass is the um, number of protons and electrons. So if the number of protons 19, so that is 39 minus 19, and then you can be able to get the number of neutron, which is 20, in this case, of potassium. So 19 plus 20 is equal to 39, which is the atomic number, the mass number of potassium. Okay, so I want you to answer the first, second, third, and fourth um, part of this table. Okay, so you can pause this video so that you can be able to answer this. All right, so let us now proceed to atomic models. So there are a lot of atomic models, so we will no longer be presenting each one. So these are the ones made by John Dalton, J.J. Thomson, Ernest Rutherford, and Niels Bohr. So um, what we will be doing right now is to focus on the quantum mechanical model done by Heisenberg, Schrodinger, Planck, Einstein, and others. And that is the one concerned by the quantum numbers. All right, so the quantum mechanical model of an atom. So the chemistry and behavior of elements is largely determined by the number and arrangement of electrons in their atom. So that's why mainly when we talk about atomic properties, we are mostly talking about the electrons, or the one that is concerned by electrons. When the atom will chemically combined with another atom to form compounds, we consider also the electrons. And since they are outside the atom, so they are the ones, no, that will be affected by any chemical reaction. So electrons move around the nucleus, though, so they keep on moving. So therefore, they have kinetic energy. So the amount of energy each electron has allowed it to occupy a defined spatial region at a certain distance from the nucleus. So later on in the quantum numbers, you will be able to say there that there are several stages, no, or level of energy or energy level wherein we can be able to find the atom or the electron, sorry. So the further from the nucleus, the greater the number of electrons that can share the space. So let us now proceed to quantum numbers. So explain the arrangement and movement of electrons, spectral lines of polyelectronic atoms, and give an acceptable model of an atom. So these are the four quantum numbers. So when we speak of quantum numbers, we're talking about numbers. So when later on, when you answer problems in quantum numbers, so the answer is number because this is quantum numbers. Okay, so there are equivalent number for each terms that we will be talking later on. So for example, principal quantum number has a symbol of letter n, small letter n. So this specifies the main energy level or the orbit. So the one that I told you a while ago, the energy level where we can be able to locate the electrons. So these are known to be as principal quantum number. So another is azimuthal quantum number or known as um, angular momentum quantum number. So azimuthal quantum number or angular momentum, they are just the same. So this talks about information about the sub-energy level or known as orbital. I am sure that you are still familiar with the SPDF, no? So later on, we will talk more about that. So magnetic quantum number, the symbol's letter M. So spatial orientations of an orbital. So if you can remember those boxes that you've made before, no? So box and then there is the upward and downward arrow. So that box known as the orbital is the magnetic quantum number. And the spin quantum number, small letter S, spin movement of electrons. So, by the way, magnetic quantum number is a symbol of M sub S. Okay? So, principal quantum number, as you can see on the illustration, no? So, for each atom, there are energy levels. So, this is equivalent to KLMN, OP, OPQ. So, up to 7 energy level. Now, for the first energy level, it is equivalent to 1. So the value is 1. Second energy level, the value is 2, 3, 4, and so on and so forth. Okay, so that means if n could be 1, 2, 3, 4 until up to 7. Meanwhile, for azimuthal, for each sub-level, the S, P, D, or F, sharp, principal, diffuse, and fundamental, there are equivalent shape. But if we are talking about quantum numbers, so the equivalent numbers there is 0 for S, 1 for P, 2 for D, and 3 for F. And for magnetic, symbol is M sub S. So as you can see on the illustration, there are orbital diagram, and there are also numbers for each orbital diagram. So S, it has only one orbital, so that is 0, the value is 0. For P, it is negative 1, 0, and 1. For D, it is negative 2, negative 1, 0, positive 1, positive 2. For F, it is negative 3, negative 2, negative 1, 0, positive 2, and positive 3. Okay, so you have to remember that for each orbital, there's only one, and there should be only two electrons that can fit inside. So one is upward and another one is downward. So later on, I'll be giving you an example on how to do this. Now, meanwhile, for spin quantum number, the symbol is M. Spin movement of electrons. Okay, so there is an upward spin, and that is um, the value is +1/2, and downward spin, the value is -1/2. All right. So by the way, let me clarify the different symbols for the quantum numbers. Principal is small letter n. Azimuthal is letter L. It is usually a slanted letter L, but sometimes it looks like a lambda symbol, and sometimes just letter L, no, without any italicized setting. And then the magnetic quantum numbers is this one is small letter M, then sub L, small letter L, right? And then for spin quantum number, it is small letter M, and then small letter sub letter S, small letter S. Okay. So again, N, L, M sub L, and M sub S. Okay, so as you can see here, this is the relationship between the quantum numbers, right? So the shells are the principal quantum numbers, so that is 1, 2, 3, 4, and so on. Subshells are the S, P, D, and F. Orbitals, um, first 1s, so that means only one electron, 2s, one electron, 2s, 2p, then another p, then another p, because for p, it is only up to 6. So 2p, 2, 2p4, 2p6, or it could be 2p1, 2, 3, 4, 5, 6. Okay? So, up to 4f. So, important numerical relationships. So, subshells within a shell is known as the shell number. And orbitals within a subshell depends on the shell type. It could be 1 for S, 3 for P, 5 for D, and 7 for F. But for each of them, we can be able to fit 2 electrons. It could be a positive, an upward spin or downward spin. So that's why it is stated there that electrons within an orbital is equal to 2. So that means that S has 2, P has 6, D has 10, and F has 14. So meanwhile, this is the configuration order. So the one that we should follow whenever we write the electronic configuration or electron configuration. So the order of filling varies electron subshells with electron follows the same order given by the arrows in this diagram. So I am sure that during your um, high school days, no, you were able to use different mnemonics. Like si Susan pumasok sa pinto, si Daddy pumasok sa door, and so on and so forth. Okay, so this one will tell you the specific location or the area for the SP, D, and F in the periodic table. So that means that those belonging to any subshell, that's the end. No, that's the end subshell for them. So, for example, the purple one, so the S area will always end with S. It could be 1S, 1S2, 2S2, 2P6, 3S2. So it's still S, no? For the D area, they will end with D. For P is P. For F is F. Okay, so there's only one for helium, which is S2, which is found on the right side, but the rest are clustered, no? P area, D area, and F area. First, S area is also clustered. However, there's one element found on the right side near the P area. Meanwhile, this is the relationship between electron configuration and the periodic table of elements, which can be the characteristics, no, the properties of the different elements. Like for example, non-metals and metals. So the one that is color green is are the non-metals, and the one in the color gray are the metals with the different characteristics such as metallic property, conductivity, brittleness, malleability, and so on. Now, in the classification by electronic properties, like for example, noble gas transition elements, inner transition elements are also color coded. Same thing as with the representative elements. Representative elements could be metals or non-metals. Meanwhile, for the periodic table groups with special names like alkali earth metal, alkali metals, halogens, noble gases are all labeled also in the in the periodic table. Okay, so this particular arrangement can tell us that the elements in the periodic table are arranged according to their property.
So we are going to write example Li lithium with atomic number of 3. So we write 1s2, then 2s1. So following the OVA principle, which is the electrons are filled up in according to a scheme known as OVA principle or building up, which corresponds to increasing energy of the subshells. Then we count 2 plus 1 electrons equals to 3 equals to the number of protons. Okay, so let us take again another example, N7. Then we write, following the OVA principle of building up, 1s2, 2s2. Then it will be followed by 2p3, completing the sequence of electronic configuration. Then we count the number of electrons given. 2 plus 2 plus 3 is equal to 7. So let us take again another example, Cl17. So we write 1s2, 2s2, 2p6, 3s2, and then 3p5. So following again our format. Then we count the number of electrons given. 2 plus 2 plus 6 plus 2 plus 5 is equal to 17. Again, protons and electrons are equal. So let us take again another example. Oxygen 8 or O8, 1s2, 2s2, and 2p4. So with that, we again count the number of electrons. To countercheck, 2 plus 2 plus 4 is equal to 8.
Okay, now, for activity 2B, I want you to write the electron configuration of the following elements: vanadium, copper, magnesium, tin, and neon. So it should be the longhand way of writing the electronic configuration.
So let us talk about the first quantum number, which is the principal quantum number. So this specifies the energy of an electron and the size of the orbital. So all orbitals that have the same value of n are said to be in the same shell or level. So these are n is equal to 1, 2, 3, 4, and so on. So in other words, n is the energy level in an atom. So let us try to draw a sample atom with its equivalent orbital. Okay, so the first orbital will represent the first energy level. The second orbital is the second energy level, and the third orbital is the third energy level, and so on. That will depend upon on the atom of an element. So let's talk about the second quantum number, which is angular momentum. So this specifies the shape of an orbital with a particular principal quantum number. So azimuthal quantum number, or italicized letter L as a symbol, is equal to 1, 2, up to number 5, wherein the subshell represents this azimuthal quantum number. So each subshell of S up to H has its equivalent number. So S is equal to 0, P is 1, D is 2, F is 3, G is 4, and H is 5. So the third quantum number is the magnetic quantum number. It specifies the orientation in space of an orbital of a given energy and shape. So the symbol for magnetic is M sub L. So this number divides the subshell into individual orbitals which hold the electrons. So the S subshell has one orbital, the P subshell has 3 orbitals, and so on. So this number has this negative 3, negative 2, 0, and positive, and going to positive 3. So as I've said a while ago, so S has only one orbital, so its magnetic quantum number is only 0. So P has 3 orbitals, so it is negative 1, 0, and positive 1. So in case of D, you have there 5 orbitals, so that is equivalent to negative 2, negative 1, 0, positive 1, and positive 2. So in case of letter F, you have there 7 orbitals. So you have there negative 3, negative 2, 0, positive 1, positive 2, and positive 3. Okay, so the last quantum number is the spin quantum number with the symbol M sub S. It specifies the orientation of the spin axis of an electron. So meaning to say that an electron can spin in only one of the two directions, either be going up or going down. If it is up, it is positive 1/2. If it is down, it is negative 1/2. So this is according to Pauli exclusion principle, which states that no two electrons in the same atom can have identical values for all 4 of their quantum numbers. So meaning to say that no more than 2 electrons can occupy the same orbital, and the 2 electrons in the same orbital must have opposite spins. So that's why one is going up and one is going down. Okay, so let us have an example for these quantum numbers. So let us take first Li, lithium, with an atomic number of 3. So first step, susulat muna natin yung kanyang electronic configuration kasi ang kukunin natin ay yung quantum numbers of the last entering electron. So we have 1s2 to s1. Now, in getting the last entering electron, so obviously yung pinakahuli, 2s1, the one with the highest energy level, which is 2. Then, yung ating s1, so kasama yung dalawa na yan. So, 2s1. So, isulat na lang uli natin para may guide tayo in getting the 4 quantum numbers. So, you have to write the 4 symbols of the quantum numbers. Yung N for principal, L for azimuthal, M sub L for magnetic, and M sub S for spin. So, dun sa 2s1 example natin, yung 2 dun, that is the principal energy level. So, that is our N. So, you have to write there 2. So, then yung S, di ba, equivalent sa SPDF, yung S is 0. So, since yung 0, yung SI isa lang ang orbital, so, ang value ng magnetic natin is also 0. Since isa lang naman yung electron, upward spin, so that is positive 1/2. So, yun yung pagkuha natin. Okay, so let us have again another example, this time fluorine. So, F9, we write electronic configuration, 1s2, 2s2, and 2p5. So, the 2p5 will serve as our last entering electron. So, we write the symbol, the 4 symbols of quantum number, N, then L, M, M sub L, and then M sub S. So, dun sa 2p5, alin dyan yung principal quantum number natin? So, obviously, yung 2. So, isusulat lang natin yung 2 dun sa equivalent ng N. Then, P is equal to 1. Diba? Kasi yung S is 0, P is 1. Then, yung P, tatlo yung orbitals niya. So, ida-draw mo lang dyan. Tatlong orbital, then negative 1, 0, and positive 1. So, di ba 5 yung electrons? So, ito-drawing mo lang yung kanilang spin. So, upward spin muna, lahat. So, i-occupy mo yung tatlo, then downward spin. So, ilan? So, dalawa. So, total of 5. San tumigil? Di ba sa 0? So, yung M sub L mo is 0, then pababa. So, negative 1/2. So, ganun lang. So, this time, baliktad naman. Ang given naman ay quantum numbers. Then, we will identify naman kung ano siyang element. Okay? So, in this example, we have N is 3, L is 1, M sub L is positive 1, and M sub S is negative 1/2. So, that will serve as our guide. So, simula muna, syempre, sulat mo yung yung pinakam last entering electrons based on the given quantum numbers. So, 3, kasi di ba N is 3. Yan. Then, L natin is 1, di ba yun ay P. Kasi 0 is S and 1 is equivalent to P. So, isusulat mo lang dyan yung P. So, 3P na yung nakuha natin. Then, magdodraw ka ng orbital. So, P yung pattern natin, so tatlo. So, negative 1, 0, and positive 1. Then, nakalagay kasi dyan, negative 1/2 yung M sub S or yung ating spin. So, then tumigil siya ay sa positive 1. So, magdodraw ka lang ng spin ng arrow up and arrow down. So, upward, then upward, then another upward ulit. So, saan ba tumigil? Diba sa positive 1. Pero downward kasi negative 1/2. Kaya isa pa ulit. So, hanggang dun sa pinakandulo. Hanggang sa tumigil ka. So, yun. So, bibilangin mo lang kung ilan yung laman ng ating orbital. So, di ba 6? So, di yun yung yung value ng P na electron. So, 3p6. Di ba? So, meron na. So, ang kasunod niyan ay isusulat mo na yung electronic configurations na ang pinakadulo is yung 3p6. 1s2, 2s2, 2p6, then 3s2, then 3p6. Ayun na yung sagot natin. So, bibilangin mo lang yung electrons. Kasi, di ba, electrons is equal to proton. Proton is equal to atomic number. Then, tingnan mo sa periodic table mo kung ano yung value. So, ayun, kita mo na, AR, 18. So, sulat mo na lang yung pinakang value natin. So, you write there, 18, the atomic number, which is argon. So, that's it. Kuha mo na agad, di ba? Dali lang.
Now, for activity 2C, this will be the last activity for this video, which you can use in practicing with all the contents or concepts that you have learned from this video. So I want you to write the quantum numbers of the last entering electrons of the following elements: cesium, scandium, zinc, phosphorus, and bromine. Okay? So, thank you so much for attending to this video lesson. So I want you to watch again the video as much as you want, so that you can be able to learn all the concepts. So see you on the next video lesson. Thank you so much and keep safe.